as we look at 31, this is one of those, there's definitely not just one right way to go. You have directions or thoughts you want to try, or that you tried, or... Okay.
I started by multiplying one side by the opposite.
To get a common denominator.
Yes. And then after I took it and started simplifying the cosecants and tangents.
Okay. And how did you work to simplify the cosecants and secants and tangents?
I did sine of x over cosine of x times 1 over sine x, or sine squared x.
So you started changing everything to sine over cosine. Okay. And then you hit a stuck point, I'm guessing?
Then, oh gosh, I don't know which way I went. There's so many.
I know, that's right. I'm just trying to decide which way I want to go with you guys. Everyone else
No,
is just
then I
saying
started
quietly,
like
so.
adding them because it was.
Okay.
Because
So,
I started adding them.
and I'm willing to try this.
And then I simplified the denominator too to 1 over
Okay.
sine squared x and cosine squared x.
So I feel like this is kind of what I got into in homeroom, where he did common denominator first, and then changed to sine and cosine, and it got kind of ugly. I'm wondering about changing the sine and cosine first,
Okay, and then doing common
and then doing common denominator. Now, am I saying that you can't do your way? No.
It just is longer, messier, more confusing.
And then, and how do I say, okay, how do you know which to do first? You don't. I mean, and that's why I'm kind of tempted to try the common denominator and see how it goes. But you might not like me for it. So, I don't know. Do you guys have a preference of which way I go?
Whatever way you
I
want.
don't know which one's going to be easier. That's the thing. That's where I'm stuck.
I was thinking we go like change this.
So all sine and cosine, and then
I
get the
say-
common denominator later.
Because
I
me and
say
Elaine were kind of
simplify.
arguing about this. Because Elaine was like, we need to get common denominator first. And I was like,
And
let's get
here's the
this
deal.
route.
They're both going to work.
Yeah, they are.
They're both going to get you there. It's just not a pretty problem. Okay. So, okay. So if we try the sine and cosine route, what do you know about tangent?
It is
Sine over cosine. Sine of x over cosine.
Sine x over cosine x over, what do you know about cosecant squared?
It's 1 over
Sine.
sine x.
Sine squared.
Sine squared x.
1 over sine squared x. Now, obviously, I'm not going to really want to leave that fraction divided by fraction, am I? So I'm going to adjust that. And how do we divide fractions?
Sine of x over cosine x times sine squared x over 1.
Okay, we're going to multiply by the reciprocal. So I end up with sine over cosine times sine squared x over 1. When we put these together as one fraction, I'm going to have what?
Sine cubed x over cosine.
Sine cubed x over cosine x. Now, before we go any farther, you didn't forget the other half of this problem, did you?
That's the
The other half of this problem, tangent x, which is
Sine x over cosine x
sine x over cosine x.
over 1 over cosine squared x.
Okay, secant squared becomes 1 over cosine squared. And then if we do the same thing, we don't want to work with fractions within fractions. So if I keep sine x over cosine x, dividing by 1 over cosine squared is multiplying by cosine squared over 1.
Sine x cosine x. Because you get 1
Over
cancel.
cosine x.
Okay. I could go two different directions here.
So you can cancel.
Okay, so one option, there's a cosine x in the denominator, and there's a cosine x in the numerator, yes?
Yes.
You have an option, you could cancel those. Now, there's a different option, because here's what I do. If I cancel those, then I'm left with sine x cosine x, yes?
Yes.
Over 1, if you will. But then, my next step, remember how we didn't get the common denominator up top?
They would
My next step is probably to get the common denominator. Well, if I don't cancel that cosine, they have a common denominator. So, unusual, but there's actually an advantage to not canceling the common denominator now. Does that make sense?
Yes.
Or not canceling the cosine. So I'm actually just going to multiply this together. Sine times cosine squared is sine x cosine squared x over cosine times 1 is cosine x. And so the advantage of not canceling this time is I get a common denominator out of it. So if we have a common denominator, what do we do?
Okay, I got there. Okay, now I'm there.
We have cosine x, right? And then my numerator is going to be
Sine x plus
sine cubed x plus sine x
cosine squared x.
cosine squared x.
So if you factor out a sin x,
You can't.
GCF of sine x, right? So if I factor out GCF of sine x on top, we did something like this yesterday in an example, didn't we? So now, if you factor out, if you have sine cubed and you factor out sine, what's left?
Sine squared.
Sine squared x.
I do that all the time.
Plus, if I have sine x cosine squared and I factor out sine,
Cosine squared.
I'm left with
you get tangent squared. Or tangent
cosine squared x. And this was all still over
Cosine x.
cosine x.
and sine squared x plus cosine squared x equals 1 from your formulas.
Do we see it?
So you got sin x times 1 over
Sine x
cosine
times
x.
1 over cosine
Okay.
x is sine of cosine.
So sine squared x plus cosine squared x, we know that to just be 1. Pythagorean identity, yes? It magically just appeared out of nowhere, it seems like.
I'm here.
I mean, it's what it seems like,
It is.
you know.
A lot of it's random.
And then sine x over cosine x
So then you have
equal to
sine x over cosine x, which is indeed equal to tangent x.
goodness gracious.
Pretty cool.
Now, was that the easiest way to get there? I don't know.
Yes.
Yes.
You know, could you have gotten there getting your common denominator first and going the sine and cosine route later? Yes. Would it have been any easier than this?
It wasn't.
Would it have been any more difficult?
It was.
Okay. I would say maybe, maybe not. Just kind of
was. This was the main one I was working on doing 4th hour when you walked by. I worked on it for like 25 minutes maybe.
Can we do 27 x?
We can.
This is the one Doug and I got into.
Okay. I think I wrote small enough I can actually put another one on this board.
I think you did.
That wasn't happening as well in my morning class.
Sine x first parentheses. Tangent x plus cotangent x. I say reduce to second parentheses.
Okay, so we have sine x times tangent x plus cotangent x.
Change it to cosine and sine.
That's what I did.
That's what I did. That's what I meant by reduce.
Looks like what I have that in my notes is changing it to sine and cosine. Again, I'm trying to think if there's a better way, and I don't know. So if we do that, okay, the sine x is just staying sine x right now because it's already sine x. What do you know about tangent?
Sine over cosine x.
Sine x over cosine x plus, what do we know about cotangent?
Cosine x over sine x.
Cosine x over sine x.
Oh, I see what I did wrong. I see what I did wrong.
Oh, now you did.
I said multiply them together and I got 1.
Common
So I added
denominator.
together.
So multiply both sides where there is
Common
multiply the
denominator.
sine x over cosine x by cosine x over 1.
common
1 divided-
denominator,
Yeah, that.
cosine x,
GCF,
sine
no,
x,
not GCF.
and then sine x plus cosine x equals 1 because of the Pythagorean identities.
What she said.
Right?
Maybe.
No, because those are square of x.
Okay, so
But when you multiply it, doesn't it make it square?
hold on.
Okay.
Okay, so the option that you guys are trying to take, which I think should work pretty well, is to take your two fractions and add them. Yes?
Yes.
If we take the fractions and add them, we need a common denominator. What is the common denominator between sine and cosine?
Sine, cosine.
Cosine.
It's going to be sine x cosine x, yes? Now, with that in mind, okay, on this first fraction right here, it already has a denominator of cosine, so what is it missing?
Sine.
Sine. So we're going to multiply top and bottom by
Sine x.
sine and sine. Over here in the second fraction, it already has a denominator of sine, so what am I missing? So we're going to multiply top and bottom by cosine. Okay. Now, don't forget, what did we have out front here?
Sine x.
We still have a sine x we haven't done anything with. That's not a bad thing. Just saying, don't lose it. So now, on the first fraction, sine x times cosine x is sine cosine. What's sine times sine?
Sine squared x.
Sine squared x. Plus, second fraction, sine times cosine is sine cosine. Cosine times cosine, cosine squared x.
You cancel the sine x, right? No.
No, the
Because
top
they're-
doesn't Pythagorean identity equal in 1.
So it's 1.
So it's 1 over sine x cosine x.
Yes.
And then you're multiplying,
And then you
and
just
then you get
left,
1 over cosine x,
which
which is to
secant.
get x.
Yes.
There's there's two big things that have to happen. And I think I heard them both. And I think, Delaney, you're just doing it in a different order. Because I think what I heard from you, did you talk about canceling your signs right now? Okay, so, and they're hooked on the Pythagorean identity right now. Both need to happen. Okay, so if we look at the fact that this sine x is sine x over 1, okay, we've got two things happening here. First of all, yes, sine squared plus cosine squared x is 1. That is true. But then also, what is Delaney noticing? Sine x and sine x have to cancel. And again, it doesn't matter which of these you do first. They both have to happen. So, let's see. I guess I'm going to keep it here for the moment as sine x over 1 times, and then this, if we use our Pythagorean identity, is going to be 1 over sine x cosine x. Since that's sine times cosine, this is where I was just saying the signs can cancel. We are left with 1 over cosine x. Don't leave a fraction unnecessarily. 1 over cosine x is secant x. Okay.
Are you checking these?
Yes, at some point.
Oh, wait. I was going to ask for an answer key, but they're in the back of the book.
They are. I do have an answer key up here, but they are in the back of the book. Which is what I'm kind of assuming at this point, if you think you had success on something,
Just check.
I'm guessing that you check in the back of the book if you haven't already. And if you didn't even get to a point of getting to an answer, back of the book isn't even going to be helpful. Okay, what other questions should we talk about?
Yeah, those are 37. I got that. 35 was just a lot of longer stuff. Which is fine. Oh, I guess we didn't do
I will do whatever helps you guys, so.
25.
I like 25. And from what I learned this morning, there are easier ways to do 25 and more difficult ways to do 25. Because how I see 25 and what some of my boarding students saw 25 as, two different things, totally. Okay? Not saying it can't work in the end, just.
I think this is when Anna helped me out in program. But she went the really easy way.
Secant squared x plus cosecant squared x minus, that's what I thought, tangent squared x plus cotangent squared x. Okay. I can't remember what my morning class did, but I did do it their way. So, let's start by removing the parentheses. Which the parentheses just say subtraction minus subtraction, yes?
Yes.
And so if it's subtraction minus subtraction, or something minus something, take that subtraction sign in the middle and distribute it. Do you see what I'm saying here? If I take this minus and distribute it and rewrite this without the parentheses, I have secant squared x plus cosecant squared x, and then it's going to be minus tangent squared x and minus cotangent squared x. So that was just me removing the parentheses there. Can you see anything?
I did.
We've already had help on the problem thus. Okay.
Because I was trying to go a different way. I was trying to go with the other options of secant and cosecant. I didn't go with the easiest one that was right in front.
And if you recall, so one of the hints I have given as we do this is anytime I see functions that are squared, added or subtracted with either other squared functions and or ones, what do I try and think of? I try and think about my Pythagorean identities. Okay, and that's what I see here, is because I see functions that are squared being added or subtracted. If we pick one of our Pythagorean identities, I can't pick sine and cosine because I don't have sine and cosine in this problem. But if I pick one of my others, for instance, one of my others is 1 plus tangent squared theta equals secant squared theta. If I manipulate this, can this match pieces up here? Does that make sense what I'm saying? In other words, what do you see up here? There's a secant squared minus a tangent squared. Can I make this look like it? Can I make my Pythagorean identity look like that? Yeah, I can subtract my tangent squared. And if I subtract my tangent squared, I'm going to find that 1 is equal to secant squared theta minus tangent squared theta. So secant squared minus tangent squared is going to be equal to 1. Well, if you need, I think you guys are seeing it, but my visual would be if I take these four and rearrange them. If I rewrite this as secant squared x, I'm going to bring my minus tangent squared x here. And then I'm going to, that means that pushes my cosecant squared x and minus cotangent squared x. Well, what do you see? Secant squared minus tangent squared is going to be replaced with 1 plus, guess what? Same thing can happen with the other one. Okay, the other identity is 1 plus cotangent squared theta equals cosecant squared theta. Well, can I make this match? Can I finagle it? And I can. If I subtract my cotangent squared theta in my identity, I can get the fact that 1 is going to be equal to cosecant squared theta minus cotangent squared theta. So right there, cosecant squared minus cotangent squared is equal to 1. What do I have up here? Cosecant squared minus cotangent squared, which is equal to 1. Challenging last step here. 1 plus 1.
4. That's what I wrote on my paper last night for the super.
And this is where my morning class, we did this one in the morning class too, and this is where my morning class said everything but 2. Just like you guys did, just on purpose, you know. Well, I assume on purpose.
11.
So, you know, I assume it was done on purpose. Who knows? Maybe our adding skills need a little bit of work.
I haven't worked on it in a while.
I'm
My brain is
gone.
instead of tomorrow's homework, I think you should give us adding problems for doing that.
Yeah, one of those addition charts that you have like a minute to finish.
I'm okay with doing them.
The mad minute problems.
Yeah.
Okay. Well, in the meantime, I'd like to do another problem here.
I did that one different too.
Did you?
Yeah. I just did the first 2. I did the secant and cosecant, swapped them, and then they canceled with the 1 plus tangent squared x, and then the minus tangent squared x canceled, and then the 1 plus cosecant x squared x, and then
I forgot about that option.
the 1 plus cotangent squared x, and then minus.
So,
Just leaves me 1 with 1.
so you're saying that when you saw secant squared here, you said, oh, well, secant squared is equal to
Yes.
1 plus tangent squared. I forgot about that option.
And then
That might have been easier, actually.
Yeah.
You might have actually had the easier route. And then over here, when you see cosecant squared, replace it with
That.
1 plus cotangent squared.
And then you don't have
And-
to extend it. They just cancel.
They end up canceling. Yeah,
Maybe you 1 plus.
that was probably actually easier.
Yeah.
And this just goes to show it's all what your brain sees, yes? For you guys, I think that was probably what Elena just said would have been easier. For me, I don't think it matters.
Yeah.
And you know, my brain was equally easy because I just paired them up and
Yeah.
but that probably would have been a little bit quicker from your point of view. Again, lots of right options.
Or in so many wrong. So many wrong.
Well, the wrong ones though more happen when you make a math mistake.
I feel like I used the whole eraser on 2 problems.
I think I'm finally getting this.
And as I said, there's a reason we're not going on to the next lesson right now, yes? It takes time. It takes practice. And if you're not practicing, it's not going to get any easier for you, but. Okay. So we have another question we want to look at.
One of the ones with pi. So either 19 or 23 or 11.
19
is easy, yeah.
23 or 11. Well,
I feel like 23 is the hardest one. Out of
probably.
there.
So 23 we go?
Yeah.
Now, let's see. 23.
Tangent. Parentheses, square root of 5 minus x. Close parentheses.
Cosecant next?
Cosecant x. Over cosecant square x.
Okay. Now, I know, Addie, you said one of the ones with pi. Notice, and I don't think the book does a very good service. Notice when I wrote that, I changed it to a upright fraction where it's pi over 2. Okay, and I did that so it would hopefully be obvious, or more obvious, I don't know, because what I see right here is pi over 2 minus x. What should pi over 2 minus x trigger in your head?
That one identity.
That one identity. Maybe you don't know the names. Maybe you don't know what it is right off the top of your head, but oh yeah, it's a one identity, isn't it? Okay.
Cotangent.
Okay. Remember your cofunction identities? Isn't that the right name? I'll be honest, I forget the names sometimes too. So right there, because I see pi over 2 minus x, and my cofunction identity says that tangent of pi over 2 minus theta is equal to cotangent. So that right there can become cotangent. I don't know if you guys want 2 steps at once, but is there something else that is
Cancel cosecant out.
fairly obvious to me? Okay, I mean, we'll get to this here in a moment, but the other thing that I see is fairly obvious is I have a cosecant x and a cosecant squared x. One cosecant x on top cancels with one cosecant x on bottom, so that means cosecant squared x just becomes cosecant x. While not done, it looks a lot better.
It does.
Okay. Now, and it could be done depending on the scenario, but this is where I would change everything to
Sine and cosine.
sine and cosine, unless you have a better option for me, but that's what my brain says to do. Honestly, I can't say that I even glanced over here to see what this says. No, I'm looking at the wrong column. It's like, that's not at all what I did. Okay, so if we go that route, what do you know about cotangent?
Cosine x over
Cosine
cosine x.
x over sine x.
All over.
What do we know about cosecant?
1 over sine x.
Well, I know something about fractions. When I have a fraction divided by fraction, the denominators are the same. The denominators ended up canceling. Now, officially, multiply by the reciprocal, right? So keep cosine x over sine x. Change division to multiplication. The reciprocal of 1 over sine is sine x over 1. And then, thus my point, if you're dividing fractions, the denominators are the same, denominators cancel. We end up with
Cosine x over 1, which is cosine x.
cosine x over 1, which is cosine x. Okay. Where are we at time-wise?
5 minutes.
Oh, we
6
still
to
have
7.
time for technically probably another quick one.
I don't
I feel like your questions have gone quicker than my morning class did.
know.
I think it's
I think so.
I had a bit of trouble with 15.
Yeah, 15. I was just about to say 15. I had trouble with that one, but then I got it.
Okay. Now I think, you know what, this page can be. I don't need those calculus notes anymore, so.
spent hours. Hours, yes.
Okay, 15. Cosine minus cosine cubed.
Yes. Cosine x.
Okay, cosine x minus cosine cubed x. Okay. As we work to simplify this, let me cover something I think I talked about in my morning class, but not sure we've talked in here. Can I subtract this?
Because they're cosine squared or cubed.
Right. They're not the same exponent, right? They are not like terms. So they're not like terms, so what do you see in common?
They both have cosine x.
Okay, so I would think in terms of a GCF here. Let's factor out a GCF.
Cosine x.
So GCF of cosine x. So if I put a cosine x out front, what is cosine x divided by cosine x? 1. Minus, what is cosine cubed x divided by cosine x?
Squared.
Cosine squared x. And that's no different than taking x cubed divided by x. Except it doesn't want me to erase my mistake. Okay, so now I have cosine x times 1 minus cosine squared x.
Pythagorean identity.
Okay. When I see trig functions that are squared, added and subtracted with other squared trig functions and or ones, I try to think Pythagorean identity. Now, 1 minus cosine squared might relate to our first Pythagorean identity. And this is where, side note, I check myself. Maybe it does, maybe it doesn't. And you don't necessarily have to write this down, but this is me trying to help you see it. Sine squared plus cosine squared equals 1. Can that be manipulated to match 1 minus cosine squared?
Yes.
Yeah, because I can subtract the cosine squared over. And then I'm going to know that sine squared theta is equivalent to 1 minus cosine squared theta. So sine squared replaces 1 minus cosine squared. So let's see, we have a cosine x out front, yes, times 1 minus cosine squared x is going to be sine squared x. And
Did you get?
this is probably about your only answer in your entire homework where you have 2 trig functions in the answer. Okay? There's no fraction here, so I can't try and go to like a tangent or cotangent, anything crazy like that. Multiplying them together is just cosine sine squared. And so, I mean, about the only thing you can do is write it without the multiplication dot, but that doesn't even really matter. So cosine x, sine squared x. All your other answers in homework go down to a trig function squared, or a number, like 1 or -1, or 2 from earlier. Okay? But none of the others, you know, we have 2 cosecant squared on an answer eventually.
Yeah, 2 cosecant squared.
But again, none of them are more than 1 trig function other than this one. Okay. So was that a good stopping point for today, I assume?
Yes. Yeah.
Have we made some progress?
Yeah. I worked on this for hours on it.